We've spent quite a while talking about least squares optimization problems now, but I'd like to move on and talk a little bit more about general optimization problems. And we're going to start by looking at unconstrained optimization. So the idea here is that we want to minimize over all x and Rn some function f of x. We call this an unconstrained problem because all x are allowed. We're not adding any specific constraints on the kind of x we're going to consider. So our primary interest is going to be to develop efficient procedures that are guaranteed to solve a problem like this. But it's easy to construct very challenging problems if we don't actually place any kind of restrictions on the type of function f that we're trying to minimize. But we'll see that a very important class of functions where we can solve this problem is when this function f is convex. I've already talked about this a little bit in the informal sense, but more formally, a function f is convex if we have that f of theta times x plus 1 minus theta times y is less than or equal to theta times f of x plus 1 minus theta times f of y for all possible x, y, and Rn, and for all possible theta between 0 and 1. So if you've never seen this definition, it might look a little complicated, but it's actually saying something quite simple. So here's a one-dimensional example. So suppose we have some x and some y, and if we think about theta times x plus 1 minus theta times y, as we sweep theta from 0 to 1, this is just sweeping over this interval between x and y, and we have some function f, and we can evaluate f at x, and we can evaluate f at y, and what this upper bound here is saying, so theta times f of x plus 1 minus theta times f of y, this is a straight line between f evaluated at x and f evaluated at y. And all this inequality is saying is that f is convex if it stays below this line. And the key is that this has to hold for any possible x and y. So anytime you pick a pair of points, if you draw a straight line between them, the function has to stay below that line. So that's the basic idea of convexity. We also have something called strict convexity, which is exactly the same thing, except where rather than saying our function f is less than or equal to this line, we replace the less than or equal to with a strict inequality. So an example of a convex function that's not strictly convex is the absolute value of x. We see that if we look at 2 points, we can draw a line between them, and the function is less than or equal to that line, but it's actually equal to it. So when we have strictly convex functions, the function f is always strictly below these lines. We'll see later why strictly convex functions might be occasionally a little bit nicer to work with. A related definition that we won't work with too much, but that's important to know, is the opposite of convexity. So we say a function f is concave if the negative of f is convex. So this is just the opposite of convexity in the sense that if we pick any pair of points and draw a straight line between them, the function stays above that line. And as I've mentioned previously in this class, we focus almost exclusively on minimization problems because anytime you have a maximization problem you might like to solve, you just take the negative of that and you get an equivalent minimization problem. And so because we're focusing on minimization problems, we won't talk much about concavity, but everything that we say about minimizing convex functions will also apply to maximizing concave ones. Just to give a few examples of convex functions, ones that we've already seen before. So f of x being equal to x squared. This is actually a strictly convex function. F of x being equal to a transpose x plus b. So this is a linear or affine function, and it is convex, but it also turns out to satisfy the definition of concave. So it is both convex and concave, and it is not strictly convex or strictly concave. And also, you will show on the homework that f of x being equal to the norm of x, where the norm here could be any valid norm. This is also a convex function, and sometimes it's strictly convex and sometimes it's not. You'll play around with this a little bit more on the homework. In the notes, you'll also see a little bit of a discussion where we talk about some useful operations that preserve convexity. So if you take a positive weighted sum of convex functions, this remains convex, and certain compositions with affine or scalar functions turn out to also preserve convexity. And these are useful facts that come in handy when you're trying to verify whether or not something is convex. But there are also other ways to think about showing that something is convex. So we have this fundamental definition, but it turns out there are other equivalent characterizations of convexity that can often be useful. In particular, when the function f is differentiable, which just means that the gradient of f actually exists for all possible x in Rn. And for differentiable functions, there's actually another way of thinking about what convexity means that's completely equivalent. So it turns out that for differentiable functions, f being convex is completely equivalent to f satisfying the following inequality, that f of x is greater than or equal to f of x prime plus the inner product of x minus x prime with the gradient of f evaluated at x prime for all x and x prime in Rn. This, again, looks a little complicated, but let's draw a picture of this. So if we have our function f of x, what this is saying is that f of x is greater than a linear approximation. And what is this linear approximation? It's basically the tangent to f of x evaluated at x prime. So if we look at x prime, and we have f of x prime here, then this linear form on the right-hand side of this inequality is just, in this one-dimensional case, a line with slope determined by the derivative of f at x prime that passes through x prime. So this is just a linear approximation to f at x prime. And for convex functions, this is always below f of x. This is an incredibly useful fact. We'll see this again later on in the lecture. Whenever you're trying to analyze convex functions, if it's differentiable, this is a very useful fact that comes up. And in fact, I think this might be the definition of convexity that we would use if all functions were differentiable. But we use this other broader definition so that we can also handle non-differentiable functions. This inequality is also relatively easy to prove. So here I'm just going to prove that if f is convex, then we have this inequality. The proof is pretty much a direct consequence of the definition we've already given. So recall that for a convex function, this means that for any theta in between 0 and 1, we have that f of theta times x plus 1 minus theta times x prime is less than or equal to theta times f of x plus 1 minus theta times f of x prime. And if we just rearrange this equation and pull f of x over to one side, so we just subtract these terms over and divide by theta, we get this expression. We notice that we have a theta times f of x prime divided by theta. So if we pull that out front, what we're left with is f of x is greater than or equal to f of x prime plus this other term. And I've rewritten it here a little bit so that it looks exactly like the form that we've already encountered. So you may recall from our review of multivariable calculus that if we look at this, the limit of this as theta goes to 0 is exactly the inner product between x minus x prime and the gradient of f evaluated at x prime. This is the directional derivative that we talked about before. And since this inequality holds for any theta between 0 and 1, that means we can take this limit as theta goes to 0, and this gives us exactly what we wanted to show. It's not too hard to show that the other direction is true as well, but you can read about this in Boyd and Vandenberg if you're curious. Yet another way of thinking about convexity, and one that you may have encountered before and remember from introductory calculus, is what we can say when f is twice differentiable, which in our case means that the Hessian matrix exists for all x in Rn. And in this case, there's yet another way of characterizing convexity, and that's that f is convex if and only if the Hessian matrix is positive semi-definite for all x in Rn. Recall that a matrix is positive semi-definite if all of its eigenvalues are greater than or equal to 0. Some common notation that we'll use in this class is this statement that the Hessian matrix is greater than or equal to 0, but where we're using this kind of curly greater than or equal to notation. And this is just simple notation for saying that all the eigenvalues of the Hessian matrix are greater than or equal to 0. Similarly, if f is strictly convex, that means that all the eigenvalues are strictly greater than 0, or that the Hessian matrix is positive definite. To give some examples of functions that we can show are convex using this definition, we can think about the quadratic form f of x equals to 1/2 x transpose px plus q transpose x plus r, where p is a symmetric matrix. You can work out the Hessian. This is what you did on the first homework. The Hessian of f turns out to be p, and notice it's equal to p no matter what x is, so it's constant. And so this definition tells us that f is going to be convex if and only if p is positive semi-definite. We've also already encountered the least squares objective function a number of times, and the Hessian for the least squares problem is given by 2 times a transpose a, which is always positive semi-definite, so this is always a convex function. But why are convex functions so helpful in the context of optimization? Well, it turns out that convex functions satisfy two really important fundamental facts that just make life tremendously easier when we're trying to find a minimum. The first is that anytime you have a local minimum, it's guaranteed to be a global minimum. And the second is a way of telling us when we found a minimizer for a convex function, which is that if f is a differentiable function, then x star being a minimizer is equivalent to the gradient of f evaluated x star being equal to 0. Something similar holds for convex functions that are not differentiable, and we'll discuss this later on in the course. But for now, let's just first dig into both of these a little bit more. Okay, so the first claim is that for convex functions, a local minimum is always a global minimum. So before I justify this a little bit more, let me first just make sure we're all clear on what we mean by a global and local minimum. So a global minimum is exactly what we've been talking about throughout this course. It's a x star such that f of x star is less than or equal to f of x for all other x in Rn. A local minimum is an x star such that there exists some small neighborhood around x star where x star is the minimum of f within that neighborhood. Formally, we want to say that a local minimum is an x star such that f of x star is less than or equal to f of x for all x with the norm of x minus x star being less than or equal to epsilon. And epsilon could be arbitrarily small, but if you can define any epsilon where x star gives us the smallest value of f for all the x in that set, then it's a local minimum. And a picture here I think will really help. So in a 1D case, this is an example of a function with multiple local minima. So right here we have a local minimum, and you see that you can define some epsilon around this point where this is the minimum of f if we restrict ourselves to looking only within this region. But this is an example where we have two local minimum, and this local minimum here is not the same as the global minimum. And there's a global minimum that does better. So note just visually, this is not a convex function, and the claim that I'm making is that for any convex function, this can never happen. So if you have a convex function, any local minimum is guaranteed to actually be a global minimum. So let's actually prove that. We're going to assume that x star is a local minimum, which means that we already know that x star is the minimizer in this neighborhood around epsilon. And what we need to show is that x star is actually the minimizer, meaning f of x star is smaller than f of x prime for x prime that aren't in this neighborhood, that are farther away from x star than epsilon. So we want to show that this is the case using convexity. So let's just recall the definition of convexity and apply it specifically to x star and some arbitrary other point x prime. And so we'll just recall the definition here. And now we're going to take a particular value of theta here. So let's take theta to be epsilon divided by the 2 norm of x prime minus x star. And remember that the norm of x minus x star is greater than epsilon, so this theta is less than 1. And also note that if we look at the norm, the distance between the convex combination of x prime and x star using that theta and x star, well, if we simplify this expression, we see that this is equal to the norm of theta times x prime minus theta times x star. And we can factor out theta. And if we plug in the definition of theta, we get that this is just equal to epsilon. So what this is telling us is that theta times x prime plus 1 minus theta times x star is actually within epsilon of x star. So it's in this region where x star is a local minimum. And so that guarantees us that f of x star is less than or equal to f of theta times x prime plus 1 minus theta times x star for this value of theta we've chosen here. And if we recall the definition of convexity above and combine these two facts, what we've shown is that f of x star is less than or equal to theta times f of x prime plus 1 minus theta times f of x star. And we actually see there's an f of x star on both sides of this inequality. So we can subtract that off and rearrange to get theta times f of x star is less than or equal to theta times f of x prime, or dividing by theta, this just gives us exactly what we're trying to show, that f of x star is less than or equal to f of x prime. For any x prime, we can repeat this argument. Therefore, x star has to be the global minimum. There's no other x prime that will make f smaller than x star. Okay, so we've just shown that if we want to find a global minimum of a convex function, it's sufficient to find any local minimum. But this kind of raises the question of, well, how do we know when we found a local minimum? So here we're going to provide an answer to this when f is differentiable. Later on in the course, we'll talk about what happens when f is not differentiable. But for now, we're going to assume that f is convex and differentiable. As I mentioned previously, in this case, it's equivalent to say that x star is a minimizer, or that the gradient of f evaluated x star is equal to 0. So let's prove this, and we'll start by doing the hard direction. So we'll start by showing that if x star is a minimizer, then the gradient of f evaluated x star has to be equal to 0. So this is really a consequence of Taylor's theorem. So you may remember Taylor's theorem. There are lots of different ways of writing out Taylor's theorem, but the version of this that we'll be using in this class is that for any u in Rn, we have that f of x plus u can be written as f of x plus the inner product of u with the gradient of f evaluated at x, plus h of u times the 2 norm of u, where h of u, this is just some real valued function that goes to 0 as u goes to 0. So this is just saying that if we have some point x, we can come up with a quadratic approximation of f by just evaluating f at x, adding a linear term, and then adding a quadratic term, and the size of that quadratic term goes to 0 as u approaches x. All right, so we're going to use this fact, and we're going to set u to be equal to some scalar t, so t is just a real number, times d, and I think of d as being some direction. And we're going to look at f of x plus t times d. And so if we just plug in t times d for u throughout this expression from Taylor's theorem, we have this. And then I'm just going to note that we can pull t out of this inner product and out of this 2 norm. And when we pull t out, we're left with this term, the inner product of d with the gradient of f evaluated x plus h of t times d times the 2 norm of d. And now we just notice, well, what happens as t gets small? So as t gets small, this h of td goes to 0, and everything else here inside of the parentheses remains fixed. And so what this is telling us is that as t gets small, this inner product, no matter what it is going to eventually dominate this expression. And so in particular, the sign of what's going on inside of the parentheses is going to be the same as the sign of this inner product. This inner product is going to be much bigger in magnitude than h of td times the 2 norm of d. So when t is sufficiently small, the quantity inside here will be negative if this inner product is negative, and it will be positive if the inner product is positive. So why am I spending so much time on this? Well, this actually tells us something very precise about what happens when x star is a minimizer. So if we plug in x star in here for x, if x star is a minimizer, that means that f of x star plus td is greater than f of x star. Well, the only way that can happen is if this quantity here inside the parentheses is positive. So if x star is a minimizer, this inner product between d and the gradient of f evaluated x star has to be greater than or equal to 0 for all d. That's what it means for x star to be a minimizer. And well, then we have to say, well, okay, well, what does this imply about the gradient? Well, the gradient, this is some vector, and we're asking that if x star is a minimizer, the inner product between that vector and any other vector in either some local region around x star, or if we're talking about a global minimum, any other vector in Rn, it has to be greater than or equal to 0. Well, it's easy to imagine if we pick some d, we'll have a positive inner product, but then it would also have to be greater than or equal to 0 when we plug in negative d. And so the only way that this inequality can hold is, in fact, if the gradient of f evaluated x star is actually equal to 0, and then we trivially have that the inner product is non-negative for all d. So this actually shows that if x star is a minimizer, then the gradient has to be equal to 0. And note, by the way, that actually nothing about this argument requires convexity. Even for a non-convex function, if it's differentiable, then if x star is a minimizer, we have to have that the gradient of f evaluated x star is equal to 0 for a local or global minimum. Now, if we want to argue in the other direction, we absolutely need convexity. So if we want to show now that the gradient of f evaluated x star is equal to 0 implies that x star is a minimizer, here we need to use convexity. So convexity, you will recall from our first order characterization, is equivalent to saying that f of x star plus u is greater than or equal to f of x star plus the inner product with u and the gradient of f evaluated x star for all u in Rn. So this is just an elementary fact from convexity, but we immediately see that if the gradient is actually equal to 0, well, then this inequality just reduces to saying that f of x star plus u is greater than or equal to f of x star for all u in Rn, which is exactly what it means for x star to be a global minimum of f. Now note that here convexity really is necessary. This is not true for non-convex functions. So here's an example of a non-convex function where it's easy to see the gradient might be equal to 0 at many different places, and only some of them correspond to a global minimum. So I just want to close this discussion on a couple of technical notes. So first, even when we're dealing with nice differentiable convex functions, it's not always necessarily the case that we can be assured that a minimizer will exist. So it's easy to write down functions where this happens. So take f of x being equal to e to the minus x and ask the question of what's the value of x that minimizes f. We'll actually see that no matter what x you write down, I can always make it a little bit bigger and achieve a smaller value. So there really is no x that minimizes f here. And this might seem like a pathological example, but you may encounter on a future homework an example of such a function. But second, it's also the case that minimizers might not be unique. So even if you do have a minimizer, there's no guarantee that there isn't some other minimizer that does just as well, right? So you may have a whole set of different possible x's that all do equally well. And so you should be careful when you're talking about the minimizer, because there might be more than one minimizer. However, there are certainly lots of scenarios where there is only one unique minimizer. One prominent example of this is when f is strictly convex. So in particular, if f is strictly convex, then if f has a global minimizer, it is guaranteed to be unique. And this is easy to argue by contradiction. So suppose that x star is a global minimizer. And for the sake of a contradiction, suppose there exists some x hat that's not equal to x star that does just as well, meaning that f of x hat is equal to f of x star. But if this is true, there are actually many different other values of x which will do even better than x hat and x star. So in particular, if you have strict convexity, you know that f of theta times x star plus 1 minus theta x hat has to be less than theta times f of x star plus 1 minus theta times f of x hat. And remembering that f of x hat is equal to f of x star, this is just equal to f of x star. So strict convexity actually tells you that for any possible theta along this line, you'll actually achieve a lower value on your objective function than what you had at x star, which is a contradiction since we assumed that x star is a global minimizer. So the picture here is just that if you take any x hat and x and evaluate the function, strict convexity tells us that if we draw a straight line between x hat and x star, the function has to stay strictly below this line, which means that x hat and x star couldn't possibly actually have been a true minimum here. And so because of this fact, the minimizer will have to be unique. Okay, so we've spent a while now talking about different ways of thinking about convexity and what the consequences are. Next time, we're going to return to talking about gradient descent as a strategy for now minimizing general convex functions. And using some of what we've discussed, we're actually going to be able to give concrete bounds on the performance of gradient descent.